Alright gang, here we go. This is for Chem 2 Unit 11. We're going to talk about buffers. We're going to have two videos about buffers. This first one here is kind of the more basic stuff, and we're going to talk about the Henderson-Hasselbalch equation. Lots of fun. Alright, so what is a buffer? Well, a buffer is a solution of a weak conjugate acid-base pair. Okay, so something like acetic acid and acetate, ammonia and ammonium, those are, those are weak conjugate acid-base pairs. And when you have them in just the right concentrations, you can make a solution that resists changes in pH. Okay, and if they resist those changes in pH, we call them buffers. Now, every buffer solution kind of has its own pluses and minuses, kind of what it's at. So here we see three different types of buffer solutions. This is a buffer solution that's at pH 10. Okay, you can see the 10 right there. And this is a pH of 7. Okay, I don't quite know why they're pointed at the whatever. There's not the color. And then this one's right. So this pH of 4. All right, right there. So anyway, so these solutions will buffer the pH changes so that they stay around these values. Now, will it buffer it forever? No. Okay, in the next video, we'll talk about, well, what are the capacities of these buffers? How do we know how far they're going to change? But for now, we're just going to talk about, well, generally, how do they work? All right, and so the way they work is they contain highly or relatively high concentrations of at least this value, 10 to the negative third molarity or more, of both the acid and the base together. All right, and their concentrations need to be approximately equal. Okay, there's two ways to make a buffer. Okay, you either mix a weak acid and the salt of its conjugate base, or a weak base with the salt of its conjugate acid. So if you wanted to make a buffer with acetic acid, you could mix, acetic acid CH3 COOH, and so that would be the weak acid, and then the salt of its conjugate base would be something like NaCH3COO, right? But that would be sodium acetate. Okay, and so if you mix those two together, you end up with a buffer, and you have to, do it in the right amounts and all this stuff, okay? Or what you can do is you can add a strong acid and then partially neutralize a weak base, or add a strong base and partially neutralize a weak acid. So like if you started with this, only acetic acid, and you wanted to turn it into a buffer, you'd add a little bit of a strong base like sodium hydroxide or something, and you would get a mixture of the acetate ion and the acetic acid, and you'd end up with that buffer solution. So those are the two main ways to make a buffer. So how do they actually work? So here you've got your initial buffer solution right here in the middle. Okay, and you've got concentration of hydrofluoric acid with fluoride ion, and they're relatively equal to one another. Okay, if you add hydroxide to this, the hydroxide will react with the acid part. So whatever your hydroxide is, it could be any base, right? Strong, weak, anything that makes water turn into hydroxide or releases hydroxide, it's going to react with the acid portion and form fluoride ion and water. And that makes sense. And then, so this fluoride ion will go up, but the hydrofluoric acid will go down. All right. Now, because the HF is there, it's going to counteract the formation of this fluoride ion, and so this pH will go up slightly, but not nearly as much as if it was just in straight water. So because we have this already established equilibrium between the acid, the weak acid, and its conjugate base, we kind of get this small change in pH as we add the base. The same sort of things happens when we add the acid. If we add some sort of acid, and it doesn't matter if it's weak or strong or anything, it's going to react with the fluoride ion, right? And so then it's going to form your hydrofluoric acid, and because of that presence of that fluoride anion is kind of counteract the formation of this acid, all right, you form a new equilibrium just slightly lower than where it was before. All right, so really it's just kind of an application of Le Chatelier's principle. Okay, so adding a small amount of acid base will only slightly neutralize one component, so the pH doesn't change very much. All right, so calculating this there's two ways to go about it. Number one, you can just use an ice table, and essentially what we just did with common ions is essentially what a buffer is, okay? But there's an easier way, and this is the Henderson-Hasselbalch equation. And this is how it's derived here. This is your equilibrium constant for your weak acid solution, Ka equals H plus A minus over HA. All right, and then if we take the negative log of both sides, you got a negative log, and then they've split this guy into 2. Okay, and remember, log, if you take a log of like x times y, that's the same as the log of x plus the log of y, and so that's what they've done here. And so they get the negative log of h, and it equals the negative log of a over ha. Now you should recognize that this negative log here is the same thing as the pH. All right, and then the negative log of the Ka is equal to the pKa. All right, so this is going to rearrange to this guy here, and this is known as the Henderson-Hasselbalch equation. This guy's a big deal in buffer world. All right, this is a really important equation. pH is equal to the pKa plus the log of the concentration of the conjugate base over the acid. And then these need to be weak acid and its conjugate base. And so this makes it really easy to calculate the pH. Now, it only works for buffers. It doesn't work for anything else. All right, but it makes life a lot easier to calculate the pH. So essentially we can calculate the pH of any buffer solution as long as we know what the Ka is of the weak acid, and then the anion and the concentration of the weak conjugate base, and it's the weak acid. All right, pretty easy. All right, so let's give it a shot here. It says, what is the pH of a buffer that is 0.12 molar in lactic acid? All right, there's lactic acid, and 0.10 molar in sodium lactate. All right, and so this would be the conjugate base of this guy. All right, and it says the Ka is 1.4 times 10 to the minus 4th. Now we know the pH. All right, we shouldn't really have this. This is just a bullet point because pH equals pKa plus log of it. Anyway, so that should be a bullet point. Anyway, pH is equal to the pKa plus the log of the concentration of the anion over the concentration of the weak acid. And so you get the negative log of your Ka, plug that in, 1.4 times 10 to the minus 4th, the plus the log of the concentration of the anion, well, that's just 0.1, and then the concentration of the lactic acid, which is 0.12. Bada bing, bada boom, plug it in your calculator, and you get the pH. All right. Now, what you could do is you could set up your ice table, and you could be, all right, well, and this is very, very similar to the problem we did in the previous video. Your lactic acid is going to react to form H plus La minus, right? And I guess we could call that HLA minus. And then you could have your ice table where you started with 0.12 of that and 0 of this and 0.1 of that, and then subtract x and set that equal and solve for your x, and then blah, 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 and you get you the same answer. All right. So here they are. They're doing the same exact problem, but they're going to do it with an ice table instead. All right, same exact problem. Pause the video, peruse it at your will, or just take my word for it. All right. We're going to save ourselves some time here. So 3.77, and then there it is. They show it in the Henderson-Hasselbalch equation again. So we can solve it using ice tables like you're used to, and take a while, or you can just use Henderson-Hasselbalch equation. Now remember, the Henderson-Hasselbalch equation only works for buffers. It doesn't work for anything else, so which is why we haven't brought it up so far. So let's try a practice problem here. Okay, it says if the pH of a buffer solution is equal to the pKa of the acid in the buffer, what does this tell you about the relative concentrations of the acid and the conjugate base forms for the buffer components? All right, well, let's give this a shot. So pH is equal to the pKa plus the log of the concentration of the base over the concentration of the acid. All right. Now, if these two are equal to each other, okay, pH and pKa, that means all of this has to be equal to 0. Well, we know that the log of, in order for a log to equal 0, that means these things here have to be equal to 1. So that means the concentration of the base, okay, has to be equal to the concentration of the acid. That's the only way we can have 1 inside of parentheses. Okay, and so so let's see what our answers here. It says the acid concentration must be 0. Well, if the acid concentration is 0, that means our log, that doesn't work. That doesn't make the base equal to 0 either. So the base concentration, well, that doesn't work. So A and B are right out. C, the acid and base concentrations must be equal to each other. Well, that's exactly what we just established. So that's probably the answer, but let's see what else we got. The acid and base concentrations must be equal to the Ka. Well, that doesn't even make sense. All right. The base concentration must be 2.3 times as large as the acid concentration. Again, that's not really what we established. All right, so we're good to go. All right, we're Gucci. Let's try this guy. All right, now it says here, all right, it says calculate the pH of a buffer composed of 0.12 molar benzoic acid and 0.20 molar sodium benzoate. So we can use our Henderson-Hasselbalch equation because we have that word buffer in there. All right, so our pH is equal to our pKa plus the log of the concentration of the base over the concentration of the acid. All right, so the pKa, so that'd be the negative log of the Ka, and I looked it up online, unless Google lies to me, it'd be 6.3 times 10 to the minus fifth. All right, plus the log, concentration of the base. Well, this is our base, benzoate, so it'd be 0.20 divided by 0.12, the concentration of the acid. So that means our pH is equal to all right, negative log 6.3 e to the minus fifth plus the log of 0.2 divided by 0.12. All right, and I got 4.4225082, 2 sig figs, so that means we go to 2 decimal places for our pH, so it would be 4.42. So there's our pH for this guy. Boom, Bob's your uncle. Cool? So easy. You know, you're like, whoa, how could it be so easy? All right, now, here's the dealio, though. Okay, we have to be careful when we're using the Henderson-Hasselbalch equation, because one of the big assumptions we're making in the Henderson-Hasselbalch equation is that the change in concentration will not affect the overall concentration. Okay, so it's the same kind of assumption we're making when we use the ice tables and we drop our plus or minus x. All right, so in this case here, we're gonna walk through here and we're gonna calculate the pH of the buffer using the Henderson-Hasselbalch equation and making no assumptions. All right, and see what we get, and so it gives us the Ka value. So first we're going to use the Henderson-Hasselbalch equation. Super easy here. pH equals pKa plus the log of the base over the acid. Ka here, and we've got the 2 concentrations. All right, and so here's the pH of our solution based on the Henderson-Hasselbalch equation. Now we're going to redo the calculation without making any assumptions at all. All right, so here they've got your Ka value. All right, Ka is equal to the acetate times H plus over acetic acid. All right, here's your formula, ice table. So you got your initial concentration of your acetic acid and your acetate, which makes sense, and they should be close to each other because it's a buffer. You're going to lose some amount of this, gain some amount of this, it becomes that. So because we didn't make any assumptions, we're going to have to use the quadratic formula. This is why I'm doing it, letting them do it instead of me, because forget that noise, right? I'm the teacher. I don't have to do that anymore. Just teasing. All right, so we get... So we got this guy here. Well, 1 times, plug all these guys in. So acetate is 1 times 10 to the minus 4th plus x times x over 1 times 10 to the minus 3rd minus x. And that's equal to 1.8 times 10 to the minus 5th. Solve for x. So you distribute, get an x squared, multiply this over, distribute again. Okay, set it equal to 0. Here's your quadratic formula. Okay, right here, solve for x, blah, 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 and you get this, 8.76 times 10 to the minus 5th is equal to the concentration of H+. So, using no assumptions, we get this as our pH. This is pretty different, 3.74 versus 4.06. Now, because, and here's where the kicker is, it's all because these two values here, this minus 3 and minus 4, are way too close to the value of the 10 to the minus 5th. All right, that's one of the reasons when we've said that rule back a couple of slides ago that our pH or our concentrations have to be relatively high. When we're talking relatively high, what we need them to be is relatively high compared to the Ka. If they're not relatively high compared to the Ka, then we can't guarantee that the pH we calculate using the Henderson-Hasselbalch equation is going to work out. These guys are, this one's only 100 different, and this one's only 10 times different than what the Ka value is. It's a problem. It's not going to work. All right, so the Henderson-Hasselbalch equation is not accurate for this particular example. All right. So let's do one more here. It says calculate the final equilibrium pH of a buffer that initially contains 6.5 times 10 to the minus 4th molar hypochlorous acid, and 7.5 times 10 to the minus 4th molar sodium hypochlorite. All right. So Ka is equal to this guy here. All right. So we can do it using the Henderson-Hasselbalch equation. All right, just for practice sakes, because we've only done one of them so far. So pH is equal to the pKa plus the log of the concentration of the base over the concentration of the acid. Now, I know it may seem tedious, but stuff like this, I always recommend just writing it out, just the whole thing each time, because it'll help you get it stuck in your head. So that'd be the negative log of the concentration of 3.0 times 10 to the minus 5th plus the log of the concentration of the base. Now the base here is the sodium hypochlorite, so that'd be 7.5 times 10 to the minus fourth. And then the acid is 6.5 times 10 to the minus fourth. All right. So the pH we get here, so we'll plug all this jazz in here, negative log of 3e to the negative fifth plus the log of 7.5 e to the minus fourth divided by 6.5 e to the minus fourth. All right, and so the pH we get using the Henderson-Hasselbalch equation, both of these have 3 sig figs for our Ka, a loser Ka, 4.59. All right, so this would be the pH using Henderson-Hasselbalch equation. Okay, now, but really, because this is times 10 to the minus fifth and both of these are times 10 to the minus fourth, we can't really use that. So we're going to use the istable here. So we go HOCl is in equilibrium with H plus OCl minus. All right, we got our istable ICE. All right, our initial concentration of HOCl here, hypochlorous acid, is 3.0 times 10 to the minus fifth. This is 0, and this is 6.5 times 10 to the minus fourth. All right. Oh, that's the Ka. I'm sure some of you guys are screaming at your screens. Right? Oh, you idiot. I can't believe you would misread numbers on the freaking... Don't you practice these before you make these videos? Only sometimes. All right, that's the answer to that. Oh, and I screwed up the other one too. Oh my gosh. All right, let's try again. Here we go. We're doing it live. All right, so 6.50 times 10 to the minus fourth, and our OCl minus is 7.50 times 10 to the minus fourth. All right, we're going to lose some amount of that. We're going to gain some amount of that. We're going to gain some amount of that. This becomes 6.5 times 10 to the minus fourth minus x, and 7.5 times 10 to the minus fourth plus x. All right, so that means our Ka is equal to the concentration of these two guys. So it would be x times 7.5 times 10 to the minus fourth plus x over 6.5 times 10 to the minus fourth minus x. All right, and that's all going to be equal to our K value, which is that 3.0 times 10 to the minus fifth that I tried to use earlier. All right, blah. We're gonna cheat here. We're gonna use Wolfram Alpha. Forget that noise. I ain't doing this on video. Everybody. If you need to help out to do quadratic equation, you've got bigger problems. Wolfram Alpha is your friend. So x times 7.5 e to the negative fourth plus x divided by 6.5 e to the negative fourth minus x. I wonder if that works. I guess we'll find out. Equals 3.0 e to the minus fifth. Oops. I fouled it up. The hive mind is going to yell at me. All right, let's see if this works. I'm not quite sure if I can type it in that way. I guess you could see.
People hate the Elder Scrolls.
Excuse me. So when I type this guy in here,
we got some classic WoW PvP
I
plans.
go.
Glorious. My name is Force. Welcome back to the Force
You
feed.
got the.
The
Oh
internet.
crap. Oh no. Shoot. This is what I get. All right. So you've got this guy here, right? And so did that punch out what I wanted it to punch out? See, this is what I get for trying at 3.07 plus x times x, 6.5 minus fourth minus x. Yeah. All right, equals 3 times. So if we solve for x here, your x is equal, we got two values here. We got one that's negative, that's no good, and then the other one that's positive here. So that's the one we're running with. So that guy here is 2.42 times 10 to the minus fifth. All right, 2.42 times 10 to the minus fifth. Good old Force. 2.42 times 10 to the minus fifth. All right, and that is our H plus concentration. So our pH is equal to that, or the negative log of that. So our pH is equal to the negative log of 2.42 e to the minus fifth. And I got 4.62. So this guy's actually pretty dang close. All right, this was 4.62, that was 4.59. So really, that one there, Henderson-Hasselbalch doesn't do such a bad job. But you really don't know for sure until you actually do the math, okay? Which kind of sucks. If you don't have the internet when you're taking your quiz or exam, but you got a graphing calculator that you're allowed to use, you can just plug this equation here in your graphing calculator. Set 1 equal to this guy on the right, or on the left, set this one equal to the guy on the right, and find out where they intersect each other. Or you could subtract this over and find out where it equals 0. 6 of one, half dozen of the other. All right. Last little bit here. Buffer capacity is defined as the amount of acid or base that the buffer can neutralize before the pH begins to change to an appreciable degree. Okay, so essentially, like, how much can we add to this buffer before it starts to change more than just a couple of tenths or hundredths of pH? Okay, and then it says using the Henderson-Hasselbalch equation, pH will be the same for a conjugate acid-base pair of 1 molar or 0.1 molar. Okay, that makes sense because it's based off that ratio of base to acid. So it doesn't matter if they're at 1 molar or 0.1, that ratio is going to be the same. However, the buffer that is 0.1 molar can neutralize more acid or base before the pH changes. So the bigger that concentration is, the bigger that capacity is going to be. All right. Now, last thing here that you need to know is that when you're looking at your pH range, the range of the pH values over which a buffer system works effectively, we call that the pH range of a buffer. The optimal pH for any buffer solution is where you have your pH is equal to your pKa. That's going to be your best place. Essentially, if you have your concentration of your acid and your base equal to each other, okay, if you have those two equal to each other and your value of your pH is close to, or your pKa is close to what your pH needs to be, then you're going to have your optimal buffer for that solution. So if you want to, so back in that slide way back before, we had those 3 different values or 3 different solutions. If you wanted a pH of 4, you'd want to use a buffer that has a weak acid base pair that has a pKa of close to 4. All right, and then if you have, if you wanted at 10, you'd find one that had a pKa close to 10. All right. So the other thing that you need to keep in mind is if one concentration is more than 10 times the other, the buffering action is poor. Okay, this means that the pH range of a buffer is usually about plus or minus pH unit from the pKa. All right, so when you're looking at some of these problems here, just trying to evaluate whether or not a pH is any good, this pH or this buffer would actually be pretty dang good because they're really, really close in values, right? They're less than 10 times different. Okay, but some other ones that we've looked at, would not necessarily be good. Like this guy here, these are 10 times different, so this would have a poor buffering action. All right, comparatively. All right, next video we'll talk about what happens when we add a strong acid or a strong base to a buffer, and then soon we will hit titrations and your life will change forever. Okay, all right, do your practice problems. I'll see you on the flip side.